تعالى, I will update the YouTube channel with the latest recordings. So I'll start presenting my screen, and we are trying to cover the remaining topics related to memory management. So first, before I want just to make sure there are a few concepts are very important. I want you just to make sure you understand well. The first concept is internal fragmentation, vice external fragmentation. So imagine in memory, inside the memory, imagine we have this area from here to here in memory. This is one process. Like for example, we say this is process 1. Okay, this is process 1, and this is process 2 from here to here. Okay, so these two processes. So this big area, okay, this is the first process, and this is the second process. Okay, I will again redraw the notations just to make sure it is clearly illustrated. Okay, this area in red, this red box, okay, it is an area in memory, okay, reserved for process number 1. Okay, from this point here to this point here. Okay, all of this area is for process 1. Now, if inside this area, inside the process, we are using only this area, the gray area here, the gray area, we are using this, and we are not using the one in white color. So the white area here, inside one process, if there is unused space, a space or a memory area not used, this not used area that is inside the process, we call it a fragment. Specifically, we call it internal fragment. Okay, so this is an internal fragment. Okay, and this is another process 2, that is from this area here to here. Okay, and the gray area is used and the white area not used. So this is another fragment. So this is, we call it internal fragmentation. The other concept is external fragmentation. External fragmentation means that suppose you have one area here for the process, okay, and you have another process in this area, and all of them is used spaces. Okay, so this is process 1, and this is process 2, and they have assigned space. Okay, all of it is used, but in between the processes, in memory, there are some spaces, area not used, unused space outside the processes, okay. So this in memory space that is outside the process, we call it external fragmentation. So this is one key terminology you should try always to remember. And the other terminology I want to mention is the segmentation. If you remember from last lecture, we were talking about paging, and we said that we can divide a process or a program into multiple processes, or the process we can divide it into multiple pages, and these pages are inside the disk, and we can then swap in these pages inside the RAM, and when we swap it inside the RAM, we swap it inside frames. So they were saying that we have pages and frames. Now, when we were discussing pages were fixed in size. They were fixed in size. Just to remind you with this, um, maybe I will go back to the okay, this one. So they were fixed in size. Every page, it has a fixed size. For example, this is an example here, and maybe more clearly I would say, where is that one? Fine. Okay, this one. So if we have a process, we can divide the process into page 0, page 1, page 2, page 3. These pages are fixed in size. All are equally, they have equal size in memory. They have, for example, 1 mega, 1 mega, 1 mega, 1 mega, or 16K kilobyte, 16 kilobyte, 16 kilobyte. Every one of it is fixed in size, and they are equally in size. When we map it inside the physical memory, these are inside the disk, okay, inside the disk, and we put it inside the physical RAM here, okay. Also, we map it inside the RAM with the same size, the same fixed size. So this is paging. So paging, we use fixed memory size for every page. But segmentation, we when we have a program that can be subdivided into segments that vary in length, that may vary in length or in size, okay, in length or in size, whatever the you say size, we say length, no problem. But the point is, we might have one segment 1 mega, the other segment is like 2 mega, and etc. So they are different in size, but we have a maximum length. We have a maximum length or maximum size. Okay. So this is called segmentation. Now in segmentation, we have some uh, details regarding segmentation, but this is the most important point I want you to remember. Okay. The last thing I want you to also try to have an idea about it is the comparison between the memory management techniques. So you need to have to understand what are the lengths, what are the strengths, and what are the weaknesses. What is the positive side, okay, and what is the negative side of any memory technique. So this table is important. I want you to memorize it. So we have multiple techniques. So we are focusing on paging, okay, and in virtual memory paging. These are the two things we are giving details during today class. But the other techniques we will not cover, but I want you to have an idea about it. So we have these techniques on the left for memory management. So this is a description for every technique, and this is the positive side or the strengths, and this is the negative side of the technique. So if we look into fixed partitioning, so the main memory is divided into a number of static partitions. Okay, static partitions is fixed size, so it is almost similar to simple paging. Okay. When we say dynamic partitioning, so the partitions are created dynamically. So it has multiple sizes, different sizes. So it is similar to simple segmentation. Okay. So paging and segmentation, or fixed partitioning and dynamic partitioning, is almost the similar things, but these are there are similarities, but in our course here, I don't want to go deep in details, but we will explain paging with the fixed size only, okay, regarding the virtual memory or inside the memory. uh, and there is the terminology of replacement. We will also cover it, inshallah ta'ala, today. Um, it is in the videos I already sent you with the link. We will go through some explanations today, inshallah. But the other techniques, I want you just to have an idea about it. What does it mean, and what are the strengths and the weaknesses? So in the fixed partitioning, they're simple to implement, or little operating system overhead. This is the positive side. The negative side, inefficient use of memory due to internal fragmentation. It might cause internal fragmentations. Okay. Um, and the maximum number of active processes must be fixed. Okay, so this is a weakness in fixed partitioning. In dynamic partitioning, we have no internal fragmentation, more efficient use of main memory, but insufficient. The negative side of it is inefficient use of processor due to the need for compaction to counter external fragmentation. And in simple paging, we have no external fragmentation, but we have a small amount of internal fragmentation. In simple segmentation, we have no internal fragmentation, and we have the weakness is we have external fragmentation. In virtual memory paging, we have no external fragmentation, okay, and we have overhead of complex memory management. And in virtual memory segmentation, we have no internal fragmentation, okay, but we have overhead of complex memory management also. So this comparison, you can go into the details also. يعني try to memorize this table, have the understanding of every description of every technique, and understand the strengths and the weaknesses. طيب. اللهم صل على سيدنا محمد. Now I will try to go through chapter 10, which is the last chapter regarding the memory management. Next week, if we have any missing topics or additional topics, I will let you know. But basically, this is the يعني I'm trying to cover all the material necessary for the final. Now, if we have to have any classes next week for theory or maybe a revision, I will let you know. طيب. Okay, now I will go through the details here. Uh, if you remember, I sent you an email with this link, okay, with this questionnaire or this question. It's a reflection. There are a few videos I wanted you to see, and before you come to class today. I hope you already did it. It's not mandatory, it's optional, but it's highly recommended because it is explaining the algorithms for you. So I will not explain the algorithms in details for you because it takes a lot of time. So I want you to do it yourself. And if you have difficulties to do it, you can get back to me any moment, okay? Don't hesitate to contact me. Right. And these are important algorithms. طيب. First of all, I would like to thank those who responded. I had 7 responses. Okay, جزاكم الله خيرا. So thank you for those students who tried to solve it. So we have the student 3820123 and 4211582, 4111438, and 3720287, and 4110205, 3720287 again. طيب. Anyhow, thank you very much and جزاكم الله خيرا. Try to solve it yourself. Now I will go through the questions and will go comments. I noticed that, mashallah, most of you are solving most of the questions here. Okay. So anyhow, I'll go through all the questions. If you have any difficulties, inshallah ta'ala, by this revision, you will complete all the points بإذن الله تعالى. طيب. So I will start with the first question here. So this is what is paging. So paging is a memory management scheme or technique by which a computer store and retrieve data from secondary storage, or we call it logical memory, or we call it secondary memory, or we call it a disk. All these terminologies is the same. Yani I notice many students get confused with multiple things. Okay, so the disks, the hard disk يعني. Okay, the hard disk mainly we call it secondary storage, or we call it also secondary memory. It's the same. We call it logical memory or logical storage. Logical memory. This is the same name. Yani. At the end, this is the disk or the hard disk. We give it these names. At the other side, we have the RAM. The RAM, okay, we call it primary storage. Primary, okay, or we call it primary memory, or we can call it physical memory. Okay, this is the different names for RAM, different names for disk. It's the same. So what does paging do? Paging is we have our program inside the disk. This program is divided into multiple processes, maybe one process, maybe two or more processes, and the processes might be also large, so we divide it into pages. Okay. Now these pages, when we save it in the disk, we might swap it into the RAM for execution. So we swap it. So this is paging. So we store and retrieve. We store and retrieve. يعني we swap it in and swap it out. Okay. So again, storing, when we say store, store is like save. Okay. The same meaning. Okay. Retrieve is like we we copy from the memory. Okay. That's it. This is the simple terminologies of retrieve and store. طيب. So this is paging. So the answer is true. So paging help prevent external fragmentation. So does it really help external fragmentation? We can go here back to this table. So we have paging. Okay. So in paging, we have no external fragmentation. No external fragmentation. So this is paging help prevent external fragmentation. Okay, it is also yes. Bye. Page faults and page fault handling. Also a numerical example and the terminology of thrashing. So what is a fault? A page fault. What does it mean? The page fault simply is when you want to copy, you want to retrieve some page from memory and it does not exist. So then there is a fault. And this is an example here. For example here, okay, we have page 0, page 1, page 2, page 3. Now all these pages are mapped. There is a reference for them inside the page table. There's a reference. It means their number is there. Yani number 0 is here, number 1 is here, number 2 is here, number 3 is here, and every number here is mapped. Yani there is another number that reference the frame from the physical memory. So every frame number 1, okay, is have a reference here inside the page table, and every page here has a reference inside the page table. So these numbers are together 0 and 1, 1 and 4, 2 and 3, 3 and 7. So we save them in the page table. What does that mean? That means if I want to execute any one of these pages, page 0, 1, 2, 3, all of them are inside frames inside the memory, and this is why anytime I want to execute them, there is no fault, because I'm already saving, these are available for execution inside the physical memory. So we can say there's no faults. But if any one of them is not available in the page table, then we say there is a fault, a page fault. Okay. So this is what a fault means. Um, for example, if we look here before allocation, we have inside the disk page 0, 1, 2, 3. These are, for example, one process, some new process divided into 4 pages, 0, 1, 2, 3, 4. And we already have 3 frame lists inside the physical memory here. That is frame 14, 13, 18, 25. Okay. So we don't have any one of the pages mapped into the physical memory, nothing yet. Suppose now the CPU or the operating system want to execute page 0. Page 0 is not available in the physical memory, for execution. In this case, we say there is a page fault. Okay, so this is the basic concept of page fault. طيب. Okay. Now, if we have okay, I want just to illustrate something here, also important for you to understand. طيب. Okay, this is the disk here, and this is the frame list here. Okay, and this is the physical memory here. Okay, so this free frame list, this is available inside the MMU, the memory management unit, a device in a hardware that save the page table. Okay, so this is the page table, our page table here. Okay, so the page table has a free frame list 14, 13, 18, 20, 15. Okay, and we want to assign for every frame a specific page number. So the pages, a specific page number. طيب ماشي. Anyhow, the page number. Okay, so we can say page 0, we want to put it in frame 14. So we put 0 here. Okay, we put 0 here. So page 0, we want to swap it in the physical memory in the free frame list number, the free frame number 14. So we put here 0. When we put 0 here, what does it mean? We copy the data that is maybe 1 mega, 500 KB, whatever the size of it, we copy it to the physical memory to be executed. Now, because page number 0 was not here in the page table, there is a page fault. There is a page fault. So we have the page fault. The page fault will be 1. We say the page fault is equal to 1. Once it is loaded there, then we can, it is available inside the RAM. Okay, this is the RAM, the physical memory يعني. So it is executed. So we can execute this code because it's available inside the RAM. So now suppose the operating system or the program you want to run, you want to execute page 0 again. So we can execute page 0 again directly because it's available in the RAM. So there will be no page faults because it's already mapped in the page table, and the data, the instructions, let's say the instructions or the program, the code is already loaded in the memory here in page 14. So we can execute all this code directly. So we have something called the reference. We call it the reference string. Where is that one? Okay. So we have something called the reference string. What does the reference string mean? The reference string the reference string. The reference string mean that what page is on demand by the operating system. So the user will want to execute some code uh, available in page 0. So the user maybe do a double click on the program. Page number 0 must be executed. The operating system will take this responsibility to execute the code. The operating system, he will communicate with the MMU and the disks and the RAM and coordinate these efforts in order to execute this code available in page 0. After it finish execution, okay, maybe the user would like to request another time to execute also the same page number 0, and then again page number 0. So the page can be executed many times depending on the request or the demand of the user, or maybe the demand of the operating system. So this is why you can have repeated pages. This number of pages that we want to execute, the series of numbers here, we call it the reference string. We call it the reference string. Okay. So after some time, maybe after we executed this and this and this, we want to execute page number 2. Okay. This is what is on demand for execution. The operating system will go to the MMU, and he will check, is page number 2 available inside the page table? So page number 2 is not there. Because it's not there, it will cause a page fault. So the page fault counter will be increased. So we will have 2 pages now. We will have 2 page faults. Then it will load it will add inside the page table the page number 2, And for example, we want to save it in frame number 13. So in frame number 13, we will have this page number 2 available inside the RAM. So it is ready for execution. It will be executed and it will stay inside the page table. Suppose after some time we requested the same page again, page number 2. So page number 2, once it is requested and demanded by the user or the operating system, we go to the page table, we find that it is available already in the RAM, so we execute it directly. There will be no page faults. So this is the mechanism, how it works. So every time there is some page on demand, it's been requested for execution. So this is why we say 00022, for example. Also in the here in the examples, we will say reference string A, B, C, D, C, A, D, B, E, B, and these letters here, they represent different pages on demand in memory. Or sometimes we give them numbers, not ABC. We say 1, 2, 3, or no problem the numbering, ABC or 1, 2, 3. It's the same with the same understanding. Type. Okay. I hope they have no questions. Okay. Type. Uh, okay. Back to the questions we have here. So pages, these pages that are on demand, okay. Uh, for example, this is a list of all pages on demand, okay. So what we can do is we can check their frequency. So how many times they've been requested. So page 0, page 2, page 3, page, okay, we have 3 pages, for example, here. Page 0, page 1, page 2. Okay, so this is the page and this is the frequency. So how many times it has been on demand, it has been requested for execution. So if we have the reference string 101203 03 again and 23032, so this is the reference string. Okay, now how many times did we request page 0? For example, we requested page 0 in this example 1, 2, 3, 4 times. Okay, 4 times we requested page 0. How many times you requested page 1? 1, 2, 2 times. Okay, how many times did we request page number 2? 1, 2, 3. So this is 3 times. Okay, last thing is page number 3. Okay, number 3, how many times we requested? It's been requested 1 time, 2 times, 3 times, and 4 times. So this is the frequency. The frequency, yani how many times it's been repeated. Now, which one of these pages is the highest in frequency? Highest. So 4 here and 4. 4 are these two are the highest in frequency. So page 0 and page 3 are the most in demand. Okay. Now this understanding, the most frequent accessed pages, we call them the working set. We call them the working set. I hope it's clear, inshallah. طيب. Also the other terminology we have here is the terminology of uh, thrashing. Okay, so thrashing is a problem that might happen inside during paging. Okay, um, it's a very simple concept. I will tell you, for example, in our example here, uh, just suppose Okay, we have here the CPU. Okay, now suppose the CPU is busy uh, to do swapping in and swapping out. Okay, but because this is also instructions need to be executed by the CPU. So suppose the CPU is busy doing swapping in, swapping out, swapping in, swapping out. Okay, and because he's busy doing swapping in and swapping out, taking the pages from the disk and put it in the physical memory, he is not executing the instructions all the time. He is busy doing paging, okay, and replacing the pages, okay, more than the time he is executing the instructions inside the RAM. Okay, he must execute these instructions, for example page 2 and page 0 here. He must execute it, but because he is busy doing swapping in and swapping out, he might not have enough time to execute these instructions that are inside the RAM quickly. He will be little slow. Why? Because he's busy doing paging in and paging out. This case, this case we call it thrashing. So thrashing, where a process, once it's been executed, it is spending more time paging than executing. This is the bottom line of it. So what does that mean? What that means is that also paging faults go up dramatically. Paging faults, then we have many paging faults. So every time the CPU want to execute a page here, this page, for example, is not available in the page table. So a page fault will happen. And another page table not available in the page table. Another fault happen. What does a fault mean? It means it's not in the list, and the CPU have to copy the data from the disk to the RAM. So every time there is a fault, the CPU have to solve it, and will have to swap in the page from the disk and copy the instructions to the RAM. So he will be busy doing copying and adding new pages, new pages, new pages, new pages. So many faults will happen. So this is why paging faults go up dramatically, and this is what causes thrashing to happen. So as I said, thrashing will have the computer system to slow down, so that, and then the less CPU utilization and less performance. So all of these are true. طيب. The next we have it here. The next video is talking about the concept of page replacement. Okay, uh, and as I said in the previous example, it's about just swapping in and swapping out the things. So page replacement is how to decide which to swap in and which to swap out, and we have to decide which one to do this and I will show you in a moment. Now suppose after we suppose we have in the free frame list. I'll just give you a simple example here. Suppose we don't have uh, in the page table, we have only two frame list free. Free frame list, we have only two, 14 and 13. The RAM is almost full. Yeah. And we have only two frames free. So we loaded page 0 and we loaded page 2 in memory. Now suppose the reference string we added page 3. So the user or the operating system want to execute new instructions that are available inside page 3. Now if we see here in the free frame, the list, it it's not no more free. It's busy now. 14 and 13 are already mapped to 0 and 2. So there's no enough free space, so we can add this page number 3 in memory. Okay, suppose the rest of the memory is busy with some other things. So what we do, shall we move page 0, here, shall we return it back to the disk and replace it with 3, or shall we select page 2 and we remove it from the RAM, we return it back to the disk, and we replace it with page 3? Which one to select? So here come the algorithm's principle. So one of the principles will say, okay, we have served this 0. We already used 0 before 2. So page 0 was used before page 2. So we already, it's been served. So the first been served, the first, we will take it out. The first one, not the last one. So we have 0 and we have 2. So we swap the one that is first, we swap it out from the RAM, we return it to the disk, and we put the new one instead. This is one algorithm. The other algorithm is the opposite. We will say, no, we don't want the first one, we will use the last one. So we will swap 3 with 2 because we requested 2 at the end, last. Okay, so this is 2 algorithms, and in between there are several other algorithms. This is why we will see some, it is already explained in the videos. Okay, so this is called page replacement. So we replace these pages, we swap it out or in according to the need. So if we have a need to allocate, so this is the page replacement. What does page fault mean? Okay, we said page fault, when we want a page and this page is not loaded in the physical memory. We want to execute or to run a page, but this page is not loaded in the physical memory. Then in this case we have a page fault. But I want you to remember also that this page fault is one type of an interrupt. So this question, answer of it is all of the above. So the page fault is an interrupt, and also it happens when we want to execute a page that is not loaded in the physical memory. Right? Okay, the next video here now is one of the algorithms, as I said a minute ago, that we want to swap out the first page that's been executed. So this algorithm is called the FIFO. So you have to watch the video and understand the example. But I added this additional question here. So in question number 1, suppose the reference string is 11111. The number of page faults using first FIFO is how much? So this is an example. We are supposing we have a reference string of 111, 4 ones. So this is an example here, and this, suppose we have three frames, and we want to see how many faults will happen. So this is the frame. This is like a copy, or not a copy. This is how we see the frame, for example, in the at time 0, and here we see it at time 1, and then how we see it in time 2 and time 3, etc. Okay, or we can say also how the frame list will look like in every point at time. So this is why we are repeating it here. Okay, so it's like we see it in different times. So anyhow, at the beginning, there is one page number 1 is on demand. Page number 1 is not available in the frame list. We did not load it in the physical memory. So in this sense, we have fault, page fault, the page fault equal to 1. So we have one page fault. Now the operating system will load it inside the frame list, and it will be loaded in the physical memory. It is swapped in the memory. Done. خلاص. طيب. After some time, again page 1 is requested again. We look into the page table, it is available, and once it is available, it means it's already loaded in the physical memory. And in this sense, there's no page faults, so we can execute it. And then again here we load again, it's on demand, it's requested to be executed, it's available, no need to do anything. And again it's requested for the last time, it's on demand, it's available in physical memory, we don't do anything. So خلاص, the code is executed from the physical memory to the CPU. So there's no page faults except the first one. So how many page faults? One. So only one page fault happens. So this is the answer of this question. طيب. The next question here, if we have A, B, C, D, we have multiple demands on multiple pages, page A, B, C, D. Okay, so what will happen is we have 4 pages, 4 frames available. طيب. So at the first point of time, there's nothing here. So we will have page A. Page A is not in the list. It's not in the physical memory. So we have to load it to swap it in. So one page fault is there. So page fault, we have one page fault because 1A is not available. So we put it here, it's ready, we execute it, خلاص, done. At another point of time, this for example time 0, after some time 2, time 3, etc. After some time, we requested B for execution. So B is not available inside the RAM. It's not available in the page table. So we have another page fault here. It will be 2. Okay, give me a second, please. السلام عليكم. عليكم السلام ورحمة الله. أي نعم، حياكم، مرحبا، تفضل. والله كان عندي محاضرات وما يعني ما خلصت إلا بعد الظهر، وجيت المستشفى بعد الظهر ما حصلت الطبيب، قالوا لي ما في عيادة. طيب، الآن أنا عندي محاضرة بحاول إن شاء الله أخلصها وأجي على طول بإذن الله. الدكتور معتصم تقصدي ولا؟ خلاص أمر. خلاص إن شاء الله أمر أسرع وقت بإذن الله. شكرا لك، بارك الله فيك. ما الله، حفظ الله، مع السلامة. طيب، السلام عليكم. معلش، عذرا. Okay, let's go back to the explanation. I had to pick this call والله. طيب. So we were saying that we have A, B, C, D. So A is not there. We have one page fault. B also is not available. So what will happen is we add B also at some point of time. So both of them are loaded, and we have 2 faults. And then C is requested. So C is not available again. So we'll have another fault, but we have to load C. Okay. So this is another point of time. So we have 3 available in memory. So we have 3 faults. Okay, last one is D. Again, it's not available. So there's another fault. So we have 4 faults, and we load the last one in memory A, B, C, D. So these are the loading of these 4. So how many page faults we have? 4 page faults. Okay. So in the case of ABCD, we have 4 page faults. Right. Optimal page replacement algorithm with example. This is another algorithm for to be for page replacement. The point here is very important. I want you to just remember. I want you to solve only question 1 until minute 11 32 second بس. يعني don't continue the video to the end. Only question 1. Because in question 2, I think there is an issue with the solution. So better not to go there, okay, please. So only focus on question 1, it's enough to understand the concept. Now, in this question, I have changed the reference string. So if we have the reference string is 10, 12, etc., and using optimal page replacement algorithm, what is the page fault probability? Okay, what is the page fault probability? Again, this is a simple thing. It's a simple thing because we have no points of time. We have to decide a difficult thing. يعني uh, this is the string here, and we have the pages. Okay, so if we requested one it's not in the memory, so we load it. 0, okay, it's not available, so we load it. Okay, 1 again, it's already available. Okay, 2, it's not available, so we load it. 1, 0, 2. Okay, and again 0, it's already available. 3, it's not available, so we load it. 1, 0, 2, 3. Okay, so everything is mapped. We load until here, but the rest here, all of them, 0 is available, 3 is available, 2 is available, 3 available, 0 available, 3 available, and 2 available. So we don't need to replace anything. So there's no decision we need to take to swap out something and we swap in another thing. So all these pages are all available, so we don't have to do anything. We don't use FIFO, we don't use optimal, we don't use anything. It's very simple thing. How many faults are there? Only 4 faults, because 1 and 0 and 2 and 3, all of them were not available at some point of time. So we have 4 faults, okay, and the rest is already available. So we cannot even do the optimal algorithm or the FIFO or anything else. There's no algorithms need to be executed because all pages are available. So this is a very tricky thing, yani, but simple. It's very simple concept. So in order to calculate the page fault probability, the probability is simple equation. It's 4 faults. We divide it by how many pages in the reference string. So 1, 2, 3, 4, 5, 6, 7, 8, 9, then 13. So this 13 pages, 4 faults divided by 13 equal to 0.31. So this is the probability. And the other thing is the percentage. And the percentage is the same probability here. We multiply by 100. It will give us the percentage. We will see another example for it. Type in LRU, least recently used page replacement algorithm. In this algorithm also, we have played with numbers here. Okay, and I wanted to see how much you understand the concept. It's the same thing. We load this string in memory. So this string, when you the reference string as this, it's the same thing here. Okay, so the same string when we load all of them in memory. Okay, so we have 4 faults again, and you have to find the page fault percentage. So here it's the same number. is 0.31. We multiply by 100, it will equal 31. It's the same. It will be 31 يعني 31% كده. Okay. So this is the percentage of the replacement algorithm. طيب. Also we have to do some comparison between these algorithms, these three algorithms. And the algorithm, when we do the three algorithms, we have to decide which one is the best. So the best algorithm is the one that has the less number of, or the least number of page faults. If you have the less number of page faults, it means the probability is less. Also, the fault percentage is less. Okay, so these numbers, or all of them, will be the least. So you can decide which one is the best algorithm by comparing uh, these statistics together. طيب. So in this example, we have the optimal algorithm is the least page faults, less than 9 and less than 7. Okay, so the optimal here is the best algorithm. Uh, we have also two other algorithms. The one is the least frequency used algorithm, okay, which based uh, on the frequencies, how many times the page is been requested, how frequent is. So the question here, in case of multiple pages with equal frequencies, what we will do? Okay, in this algorithm it says we want the least frequently used. So if you remember this table, okay, this is a list of pages, and here is frequency. I wrote the frequency. Now the least frequently used is this one. It has been requested or on demand for 2 times. This is the least. But suppose we have two pages like this one and this one, they have equal frequency. This has been requested 4 times and this one is requested 4 times. So which one to select for replacement? Which one to select for replacement? So the answer is we implement the FIFO. We implement the FIFO. So the first one we see it in the string here. The first one we see it here is the one we select. So we have 0 and 3. Which one come first? The 0 or the 3? If we notice here, 0 come here, it is the first, and 3 come later. So we select the 0. So this is the most important thing is about the FIFO. And the last one here about the second page replacement algorithm. So it means we have, so it is similar to the FIFO, but does not replace the victim page from the first time. So it is a true question. So the page that we replace, we call it the victim page. The victim page. And I remember we already explained it last time. Inshallah, I think so. There's one illustration. Anyhow, the point is, if I want to select a page to replace with this page, we call it the victim page. Allahumma salli ala Sayyidina Muhammad. Yeah, this one. Okay. So as I said, for in this example, we have page 0 and page 2 already loaded in the system, and the frame list, suppose it is full. خلاص. We have only 2 frames available. The rest are occupied. So if we want frame number 3, we want page number 3. Page number 3, if we want to do it here, we want to select either 0 to swap it out, we return it to the disk, or 2 to return it on the disk. We should select 0 or 2. Which one to select? We might have to decide in order to execute 3, because 3 is on demand. So we have to select which one to return back. So if we selected 0, 0 is the victim page. If we selected 2, 2 is the victim page. It depends on the algorithm you are using. So this is the thing about the victim. Now the second chance algorithm is, it says, for example, if we are implementing FIFO says we have to select the first one. So the first one is 0. So this is the first one been selected. In this case, we replace it 3 with 0. Where we replace 0 with 3, the new one. Uh, so the victim page is 0. Okay. This is the FIFO. In the second chance algorithm, it says no, leave 0. Okay, because and give it a second chance. So we keep 0 and we replace it the next time. Okay, we don't replace it directly. Okay, so this is the concept of second chance. It's a FIFO, but we give a second chance for this not to be replaced. Okay, that's it for this. That's it for this algorithms thing. I hope, inshallah, you have had a better idea about it. I encourage all of you to go through these videos, please, because your quiz is on Saturday, and by next week I want to make sure all of you have a good understanding of memory management things before the final exam comes. Okay, best luck for everyone and good luck for all of you. Inshallah, may Allah subhanahu wa ta'ala give you the best, inshallah. Enjoy your weekend and keep in touch. Um, well, the chapters in the final, all the chapters, right? If any topic will be not included in the final, any topic will not be included in the final, I will let you know. يعني I will give you, for example, um, شوفوا يا اخوان my way of teaching is, there is PowerPoint slides, okay, that is available between the students. Okay,